Okay, so the differentiation of 1 or 2 to the power minus 1, okay, d by d are 2, so this will be minus 1 or to the power minus 1 minus 1, okay, so this will be minus 1 over h 2 pi l or 1 over r square. This is equal to 0, okay, equal to 0. So here now in these two terms, 1 over 2 pi L is constant, right? So what is left inside? 1 over K R2, 2 pi L is constant. Here, what is left? 2 pi L is taken out, only H, right? R2 square.
After we differentiate the whole cube, the resistance, but
Yeah, the whole cube, but again that is constant. So we are differentiating only the resistance part because resistance is minimum here. Okay. So R2 will be equal to K by H. Right? Because here again you can take R2 common. That will go here and this whole thing end up 0. So at the end, that is what we want to find out. At this condition, critical radius of insulation is given by K by H. That's what we need. Okay. Okay, derivation is also here. You can go through. It's not that difficult. Okay. We started from here. We wrote its equation. Heat transfer equation from T1 to T infinity. Then we see here in the denominator, this is the thermal resistance for the conductive part, that is the thermal resistance for the convective part. And in both of these terms, you see here R2 is in the numerator, here R2 is in the denominator. So by increasing R2, one thing is increasing, the other is dropping. So that's why we get a curve like this, right? Initially, by increasing R2, overall heat transfer increases, which is maximum, then it starts to drop. Now we are interested, what is this condition? So in that equation, we differentiate this resistance and put it equal to 0. Differentiate means what is changing from here, it is actually R2 which is changing for a fixed R1. So that's what we did. We differentiated R2, this resistance with respect to R2, put it equal to 0, and finally we end up this. Okay, so this differentiation steps are also here. R2, which is R critical, is given by K by H. What is K here? Thermal conductivity of what? Of insulation, right? Thermal conductivity of insulation, and H is the outer convection coefficient. Okay, let's take some typical values. For example, insulation is will be less than 1 normally. Insulation materials which we use, we have it in the next slide, some typical values of K, right? That is called critical radius of insulation. Okay, so now critical radius of insulation will be higher as K increases or H drops. If H drops or K increases, this critical radius of insulation will be larger. Larger means, for example, this term is for 2 in one case, but if K is higher, H is lower, it may be 12 critical radius of insulation. Okay, now let's see typical values. Typical values like this one. Now let's assume there is a steam pipe in this room. Steam is flowing through this pipe and it is insulated. In this room, what will be the convection outside? air convection, natural convection. So for natural convection, H will be in this range, very small h, 5 watts per meter square per degree Celsius. So let me say if this is 5 for natural convection in normal ambient air. And K for insulation, he is taking a value of 0.05, some insulation, 0.05 watts per meter per Kelvin. Here it's a mistake, it's watts per meter per Kelvin or Celsius. Okay. Students were asking, few students, just before the exam, should we convert Celsius to Kelvin? I don't know from which section. So this is a long time ago. In chapter 1, we have discussed these things. Okay. Okay. Now we can find out what is R critical. It comes out to be just 0.05 divided by 5. How much it is? It is 0.01 meter or 1 centimeter. So how much is 1 centimeter? This much, right? 1 centimeter. Okay. But if you are using a pipe of 2 centimeter radius, inner radius of 2 centimeter, then what this mean? Your R1, look, now in this case, we have calculated R critical as 1 centimeter. The pipe which we are using, it has R1 2 centimeter. Now R2 will start. So what this mean? So there will be only heat drop. We are already here. Okay. For this K and H value, our pipe inner diameter or inner radius is already greater than critical radius of insulation. So you are already in the safer region. Just increase insulation without worrying about this thing. Clear? Yes, if K is high. But why K will be high? We are using insulation. If you are using it for insulation purpose. Okay. Now let's see. It's clear. If H is not 5, it's not normal ambient air without fan. If there is some fan running outside. So H will increase if it is forced convection outside, not natural convection. Then this H will increase maybe up to 50, maybe 100, maybe more than this. So what is the effect on R? If this, the R will further drop. R critical will further drop. So it may end up that you have such high force convection, this R is coming out to be 1 millimeter. So you will never be using 1 millimeter diameter pipe in any application. So
what's the matter of the arm particle increase or decrease?
oh, sorry?
What's much better if the arm particle increase or decrease?
Look, what is the purpose of using insulation?
To avoid heat transfer?
Yes, to drop the heat transfer, right? So in that particular application, for example, you are using a pipe of diameter 1 centimeter. Okay, 1 centimeter. Now you want to find out, you want to avoid this thing.
Want to avoid it.
Why you want to avoid? Because you want lesser heat transfer by adding insulation. Okay, so you want to know what is this point, and we have this formula K over H. So whatever insulation you are using and whatever is the H in that ambient, use these values to find out critical radius of insulation, and that comes out to be 1 centimeter. And your inner radius is 1 centimeter, the pipe which you are using. It means by increasing insulation, heat loss will drop. So it's good. But if you were using 0.5 centimeter and critical radius of insulation comes out to be 1 centimeter, so now the insulation thickness must be larger than this. Because you are here, by increasing insulation thickness, heat loss will increase will reach the maximum, which is at 1 centimeter. So if you want to reduce this much heat, so this radius should be used. You want to avoid this part. Okay, but in practice, normally the pipes which we are using, all right, in steam power plants or other applications, those are much larger than this radius. And also, if there is forced convection, this will reduce critical radius of insulation. All right, so you do not need to worry about this. Then, which application this concept is useful? Look here. What is this? Electric wire. In this wire, inside you have small wires, right? In those small electric wires, what is the diameter of the inner wire, copper wire, in which electrical energy is flowing? Very small, maybe 2 mm, 1 mm, 2 mm, 3 mm. And what is the purpose of that insulation? To avoid what? We want to avoid heat transfer, or we want to avoid electric shock. Then what is the major purpose of this?
Yeah.
Electric shock, not heat transfer. Okay, so in these electric wires, the radius is very small. Now R1 is here, 1 mm, 2 mm. Now by adding insulation here, and there is a heat produced in this wire, electric current flows, there is heat produced. And here we are using a very small thickness of insulation. So in that case, we are less than 1 centimeter, right?
Not refusing.
Now, here we want that heat should dissipate. Here for electric wires, we actually want that this heat should be dissipated. Otherwise, this heat will be accumulated. So here, in these cases, will be in this room because radius is so small. And by increasing insulation thickness up till our critical end, normally in these cases, we are in this region. And there we actually want that heat should dissipate, but not electric current. Electric current should not pass, but heat, if it is dissipating, it's good for their life. So in case of electric wires, okay, yes, we are definitely below critical radius of insulation. Okay, so hopefully this is clear that has been discussed. We have discussed all these points, just go through by yourself. We derived the correlation of critical radius of insulation for a cylinder. Similarly, you can also derive it for sphere. So for sphere, it comes out to be K over 2H or 2K by H. I do not remember. It's K over 2H, I think. So by following a similar procedure, you can derive it for sphere. Okay, critical radius of insulation. It's not K by H, it's K by 2H or 2K by H. Okay. So that's your home assignment, which you do not need to submit, just a part of your course. Let's do one problem. So if still you couldn't understand this concept, so with the help of this problem, you will definitely understand what this means. You see in this air conditioner, between inner unit and outer unit, whatever is the pipe connecting, it is insulated normally. And there, that insulation, you do not need to worry about this concept because your inner radius is quite high. Keep based on that typical K and H values, right? So here you do not need to worry about whatever you want, you can put. It will reduce the heat transfer. Okay. So that's why here you see a problem of electric wire, not pipe flowing through a pipe, fluid flowing through a pipe. So what is it here? A 3 millimeter diameter and 5 meter long electric wire. 3 millimeter diameter means R1 is 1.5 mm, 3 millimeter diameter and 5 meter long. 5 meter long electric wire is tightly wrapped with a 2 millimeter thick plastic cover. 2 millimeter thick plastic cover means, now what is this R2? 3.5 millimeter. Okay. Its thermal conductivity is given. This plastic, which is tightly wrapped around this wire, is 0.15 watts per meter per degree Celsius. Electrical measurements indicate that a current of 10 ampere, so here current flowing, I of 10 ampere, passes through that wire, and there is a voltage drop of 8 volts, means I know Q dot, yeah, 80 watts, that is the heat which is produced in that wire. Okay, if the insulated wire is exposed to a medium, this insulated wire is exposed to a medium at 30 degrees Celsius, means T infinity outside ambient is 30 degrees Celsius with a heat transfer coefficient H outer is at 12 watts per meter square per degree Celsius. Determine the temperature at the interface of the wire. Where is the interface of the wire? At R1 or R2? Yeah, interface. This is wire, solid wire. It's not a hollow pipe. It's a solid wire. And that is the interface. So at this interface, temperature we want to find out.
So before we find that temperature, we have the first radius as R1,
Yeah.
right? Before we go to the insulation, that radius we should have for it thermal conductivity or wire only individual.
Thermal conductivity of the wire.
Yeah.
Actually, we are
The boundaries of the wire.
Yeah, we are starting from here. Whatever heat is produced, that heat is given in that wire. Okay. If you want to know, I should start from here. So what is that thing? It's just a point. This whole wire is producing this much heat. Okay. So we are starting from here. Here the wire is shown much bigger. Actually, how small is this wire? Okay. So thermal conductivity here, thermal conductivity of the wire, why we need it? Because this wire is producing this much heat because of this current and voltage. Now this heat is flowing from the outer surface of the wire towards outside. So from this wire onwards, whatever is the thermal conductivity, that will count. How much heat will flow now. Okay. All right. So what else is given? Determine the temperature at the interface, means T1. All right, under steady state. Also determine whether doubling the thickness, if we double this thickness, whether this interface temperature will increase or decrease. That's what increase. So we need to find out. Okay. So first part is to find out this T1. Thermal resistance network is already shown here from T1 to T infinity. How many resistances? Yes, first is conductive, second is convective. So we already know what is conductive, log of R2 over R1, 2 pi K L. Okay. If you practice these questions, you will learn, you will memorize these formulas. This one, H 2 pi R2 L, right? So is equal to Q dot whole divided by T1 minus T2. T infinity, yes. Only unknown here is T1, Q dot is given. R1, R2, thermal conductivity of insulation, length is given. 5 meter, yes, given. If not given, you can do it for 1 meter. Okay, so from here we can find out T1. Okay, any question? So let's see what is T1. So after solving, T1 comes out to be 105 degrees Celsius. Okay, so this T1 we have calculated as 105. Now if you want, you can also find out T2 if you are interested. Solve from here T1 to T2 or from T2 to T infinity and we can find out T2. But here we are not required to find out T2. T1 is now 105. Ambient is 30. So it's quite hot actually here. Now the next part. If we double that thickness, means double means this will become 4 mm, means R2 will become 3.5 plus 2, 5.5 millimeter. This will be your new R2. We can repeat the same thing to check what is T1. Or, yes, we know R critical is given by K by H. So either just put R2, this new R2 and find out new T1, or just check from here by adding insulation whether temperature will drop or not. Okay, so what is K? 0.15. What is H? 12. So how much is the critical radius of insulation? I think it is 12 millimeter, comes out to be 12 millimeter. Look, critical radius of insulation is 12 and your R2 is 5.5. So you are below critical radius of insulation. So it means by adding insulation, heat loss will increase. But in this case, heat is fixed. Q is fixed. When Q is fixed, it means temperature will drop. Amount of heat which is produced here is fixed or not?
Yeah.
It's fixed. So by increasing radius, we know it is below critical radius of insulation. So by adding this insulation up to 12, what will happen? Heat transfer will increase, but heat transfer is fixed. So temperature will drop. Temperature of that inner surface will, because amount of heat is fixed, 80 watts. So it means temperature will drop. That is the second part. Determine whether doubling the thickness of plastic cover will increase or decrease this interface temperature.
So can we do it mathematically?
Yeah, you have this mathematic equation. This is mathematics. That is the formula. Put it that Q80 watts, solve it again, and you will see T1 will drop.
Q is increased, but Q is fixed.
Q is fixed.
So how?
So where this effect will go? Here, somewhere. T infinity is fixed. So it means T1 has to drop because you are increasing R2, keeping the Q fixed. But the effect of Q is different here and here. Which one is dominant? This one is, yeah, this one is dominant, convection.
But there's still the same Q dot. It's fixed, so we don't control the heat transfer losses. We didn't control the heat transfer losses.
Yeah, but we didn't want to control. We want to control this temperature. This temperature should not be 105. We want this temperature to be lower. Heat transfer is fixed. When IV product is fixed, how Q will change. But what you can do, you can control this T1. And by adding insulation, yes.
The ratio is fixed, so the denominator is in plus.
No, it consists of two parts.
The resistance is decreasing.
One is decreasing, other is increasing.
But
the whole is decreasing.
So also the upper one will be decreasing, so T1 will be.
Yes, you can understand it by any way. Because we are below critical radius of insulation. If you go above critical radius of insulation, the same thing changes. Okay. So that is, so here we checked by comparing it with critical radius of insulation with Argon. Okay. And you just need to comment here whether temperature of this interface will change, increase or decrease. That's what we were asked. But what is that temperature, new temperature, we can find out from here. Right. Right. In case of electric wires, Q gets fixed. So it is about the controlling the temperature. Right. Okay. This question we'll solve in the tutorial class, okay, in this week, because I cannot do the other experiment of convection because we need to cover the next topic. So I will do it in the tutorial class. The next topic is very important, heat transfer from finned surfaces, because we have an experiment involving fins and convection. So convection, of course, it's still after a few weeks we will start convection, but before that, at least we should cover this fin part. Okay, so this week, tomorrow, we'll solve that numerical and also a numerical from the exam. If one was from the slides, but the other was from the exercise, and that is a bit tricky question. I have uploaded the solution. Okay, so next topic. Next topic is heat transfer from finned surfaces. Finned, what is fin? So let's see. This is a wall. On this side, there is some combustion going on, maybe. So on this side, you have very high temperature because of some combustion. And the purpose is to transfer this heat so that it remains in a reasonable or bearable temperature, the wall. Like for example, here you have 500 degrees Celsius or 300 degrees Celsius. On this side and on this side, you have ambient. Okay. So there will be a heat transfer Q dot. Okay. So now let's take this part from this edge to ambient. So this Q dot is given by from this edge to this fluid. What is the equation? It's all convection, neglect radiation. So it's by convection, H A delta T. Okay. It's a metal wall, a very thin metal wall, so this will also be 500. Right. Neglect this conductive resistance. Okay. This wall could be a wall of engine, right? Engine cylinder or radiator pipe, right? And here the purpose is to increase this Q. We want maximum heat to be transferred. How we can increase this Q? Now there are three terms. Let's see one by one. One way to increase this Q is to increase this H. How H can be increased? Yeah, instead of having natural convection, use forced convection. So forced convection means use fan if it is air, or if there is liquid cooling, use some kind of pump which creates that turbulence. We go into the turbulent field. So one way to increase Q is increasing H. But in some cases it may not be practical. For example, air, you can install a fan, but to increase H in forced convection region, you can increase the velocity as much as you want. So it means higher power fan you would require. If you want to keep on increasing this H, you have to keep on increasing the velocity of air. And so it means high power fan. Now high power fan means you are consuming more energy, right? Or it will be more noisy also. If you use a very high power fan in this air conditioner, it will be may become very noisy. Okay. And also when you have air on this side, you cannot go into hundreds and thousands for air. For liquids and for phase change, we can get H to 1000, but with air, even with forced convection, H will not be in hundreds or thousands. Few hundreds you can achieve, maybe maximum. Okay. Okay. What about this one? Saturated fluid? No, we are talking about the air side, ambient side. In this air conditioner, what is the ambient? Air on the inner unit and also in the outer unit. In radiator, car radiator, what is the cooling fluid? Water is losing heat where? In the radiator. Air. Again, air. Can we replace air with something else? Yes, we can, but it will be very expensive. You will be using another water stream, and then you have to cool that water. Okay. So it means air you must use, but with air you have certain restrictions. You cannot get very high H. So when this gets fixed, then let's see can we do something here? Theoretically, yes, increasing delta T.
What's in the real life, we can't control it.
Yes. So, okay, so that gets fixed. So what is the only option left? Area. Yep. So I'm making that story. You know what is the issue, but just to make that thing. Okay, so it means the only option is to increase that area. Surface area through which heat is transferred. So on this surface, now if you increase heat surface area like this, you install such extended surfaces. Extra material is attached. Extra material means now if you see in 3D, you have extra area of heat transfer. The same air is now coming in contact with a larger area. Right? Like in the AC, you see in that AC, there is a pipe like this one, right? But on this pipe, to increase the area, there are two ways. Keep on increasing this length. Yeah, it will be much larger, but you have a limitation about the volume. In your car radiator has to be fixed in a very small volume. So you increase the area like this. You use small metallic strips over the surface of that pipe. Okay. These are called fin surfaces or extended surfaces. So the overall area is the overall methodology is to increase the area, heat transfer area, so that we can get maximum heat transfer. That's why we use fin surfaces. So if you open that box, what you will see, hundreds of fins If you open your radiator, you see hundreds of fins. There are so many fins. You have to locate the pipe. There are so many fins attached. Without these fins, this area needs to be very, very large if you are only using the pipe without any fin surfaces. That's why that's a very, very important topic in majority of mechanical engineering applications where you have space limitation and you want maximum area to deliver a certain amount of heat. Okay, what is the amount of heat we want in from this air conditioner to be taken out? It's the cooling load of that room, right? To keep that room at 25 degrees Celsius, outside is 45. You need to remove a certain amount of heat. For example, this heat which you need to remove is, for example, it's a 2-ton AC. So 2-ton AC means 3.5 into 2, 7 kilowatts. So now you know what this Q is, 7 kilowatts, which must be removed. Now you have to play with this thing. Okay, you have certain limitations. This cannot be increased, these two, then increase area until you reach your desired Q dot. Okay, so that is the next topic. So we have discussed the basics which are written here. Okay, go through by yourself. So we are using such extended surfaces which are called fans, right? Fans not only used in these mechanical or thermal systems, those are also used for cooling of electronic equipment, right? So fans of many different sizes, shapes can be used, right? Whenever the fluid flowing, or here, those are attached to some electronic circuits for their cooling, okay? Fans can be of such shape. These are rectangular type fans attached to such pipes, right? Like this one, this could be a cylindrical type of fence, right? So this is the topic. Now let's derive equations for heat transfer through fins, because what we are interested to know, how with installing fins, what will be the rise in Q, right? That is our main purpose. When there were no fins, how much was Q? When now by installing fins, how much Q is increased? So it means we need to derive the equations for heat transfer through these fins, right? So here is a general schematic of a fin attached to some surface is shown. Now heat will transfer from the surface to the fin, and then from the fin to the air, to the normal ambient air. So here the analysis which we will present is based on certain, again, assumptions. So what are those assumptions which we have used to derive those equations, which we will study now in this course? Now let's go through those assumptions. First of all, again, we are assuming 1D conduction within the fin. Heat transfer is by conduction in one particular direction. There will be heat transfer by conduction in this transverse direction, that is called longitudinal, that is transverse. So we are only considering conduction in longitudinal direction. So 1D conduction, that is assumption number one. Second assumption is, again, we are assuming steady state. Third assumption, throughout this fan material, thermal conductivity is constant, it's not changing. Fourth assumption, temperature changes, I already told you, it's 1D means this thing, that in transverse direction, heat transfer is negligible.
It's not like chapter 2, this is cylindrical, concept the geometry in the radial.
Yes, if it is cylinder, then radial. But there could be many different types. If it is a rectangular shape, then x-axis or y-axis. Yes, you're right. But here, it's not radial. Actually, it is z direction. Even if it's cylinder, we are not considering radial. We are considering this direction, z or axial direction. Okay, radiation, we are still, thanks God, we are neglecting radiation so far. Otherwise, there are so many non-linear terms comes into play. So under these assumptions, we shall now derive its equations. And we will see, and even under these assumptions, this derivation becomes so complicated. Okay. So now, again, what we do, we take a differential element of that fin, and let's write all the energies entering and leaving that element. No heat generation, no storage. So here is that small element which is taken out. So that is the heat entering by conduction in x direction, heat leaving by conduction in that direction. What is the area of heat transfer by conduction?
AC.
AC. What is AC? C means here
Cross-section.
cross-sectional area. This is the heat transfer, and the area perpendicular to this heat transfer is cross-sectional area. So for this circular shape, what is this cross-sectional area?
Square.
Cross-sectional area
Square. Cross-section.
pi r square, not pi dl.
Oh.
Pi r square. Pi d is what?
Circle.
Circumference or perimeter. So, but there is a heat transfer by convection from that surface. There is a fluid. So this heat transfer is taking place from which area?
Yeah.
Surface area. So for convection heat transfer, we are using surface area. For conduction heat transfer, which area? Cross-sectional area. So one is cross-sectional area for conduction, surface area for convection. So that is the heat entering. What is the heat leaving? Qx plus dx, and convection. Radiation we are neglecting. Okay. So now we can write its equation. E in is equal to E out, no storage. So what is E in? Qx. What is E out? Qx plus dx plus dqc from that differential element. That is the general energy balance equation applied to this small element of the fan. Okay, so now let's write what is Qx by conduction. That is conduction, no? Within that fan. Heat transfer is by conduction. So we know minus K, but which area?
Cross-section.
Cross-sectional area. dt by dx. What will be Qx plus dx? That differential change which we discussed in chapter 2. Qx plus dqx by dx into dx. So put value Qx, and the same Qx is also here. Okay, now it makes things interesting. Look here. What about cross-sectional area? For that fin which is shown, is it changing with respect to x or not?
Yeah.
Right? So AC is not constant. AC is changing with respect to x. We will assume constant later on, otherwise it will be very difficult to solve at this point. Okay, so Qx plus dx is clear. Now what is dqc? Convection. From which area? Surface area. So H, this differential surface area, into T, whatever is the temperature at that point. Temperature of the fin minus T infinity. So these three equations are clear. Now we will put it in the main energy equation. Heat entering, heat leaving. Entering by conduction, leaving by conduction, leaving by convection. So put it here. Qx here and here. So after putting it and after simplifying it, there are two steps which are not mentioned here. We can do it, of course. In any ways, this Qx will cancel with the first Qx here. Look, Qx minus K AC dt by dx. This is Qx is equal to Qx plus dx is this whole term. This term will cancel with this term. So what is left? Only this one plus with the convection. Okay. So the shorter form after cancelling is given Now, I told you AC is not constant. So here, how you will differentiate it? By applying product rule of differentiation. Because AC is a variable, this itself is a variable, dt by dx. So it will be what? Apply dAc by dx into dt by dx plus AC t square t by dx square. That will be this one. Okay. Here, yeah, it will come as it is. DAS. Okay. AC is varying, that's why this will become. Now he is dividing AC throughout, he is dividing with AC. Okay, so from here to here it's clear. Now, this is the equation which we need to solve, this differential equation. Now we shall further simplify this equation. Here we are showing a fin with varying cross section. But let's solve this equation not for varying cross section, but for a constant cross section, such fins. So what this will do, it will make our life easier. Not, yes, easy, a bit easy, that we will have this term, change in cross sectional area with respect to x is 0. So now we are left with 1, 2 terms. Okay. If we say the cross sectional area is not changing. Okay. So now, and also, what is the temperature at the base where the fin is starting? We can say this is known, this is fixed, T at base. T at x is equal to 0 is some constant value, TB. Okay. And we are saying that cross-sectional area variation in the x direction is 0. Secondly, what about the surface area? Surface area is given by perimeter into x. So I can write surface area as P into x, and in that equation we have dAs over dx. dAs over dx will be equal to P. In that differential equation, we have dAs over dx. So d over dx of px, P is for a constant cross section, P is also now fixed perimeter. That's why it is P. So now in this equation will reduce to this form because this is 0. Okay. dAs over dx, I'm saying it is simply P. Okay. Yeah. So now it is further reduced this equation to a manageable form. Okay. Because we are not mathematicians, we want to reduce it to the simplest one, the mathematics which we can do. Okay. Now some more adjustments we can do. What is this HP over Ka?
Boundary condition. Have a boundary condition.
Yes, now we'll see, but let's further reduce this equation to a form which we know, more neat and clean form. Okay, so what is this term? This is all constant, H, P, Ka. For a certain fluid environment, H is fixed, perimeter is constant, thermal conductivity is constant, cross-sectional area is not changing. So this is a constant. I am defining this constant as m square. And also I am using another term. I am defining theta as T minus T infinity. Okay, so what will be d theta by dx? dt by dx, which is changing with respect to x, and that is constant. D square theta by dx square is d square t by dx square. So I can replace this thing with d square theta by dx square, and this term with theta, and this term with m square. Now this equation looks much better, which we can solve. Now go to your old mathematics notes if you have. This is a differential equation, second order, homogeneous, linear differential equation, and the general solution of this one. If I don't think you would remember, yes. This T minus T infinity is taken as theta, where temperature is changing only in x direction, okay? So this equation is a linear, homogeneous, second order differential equation.
The E
Yes,
configuration of that.
yes. The general solution of this equation is, so after applying so many assumptions, now we have a simple form for a constant cross-sectional area fin with steady state. So here is the general solution of this differential equation for a constant cross-sectional area fin. Okay, now the general solution is here. Now we need to find out C1 and C2. E to the power mx, we know what is m. We have defined m as under root of hp over ka, constant. Okay, now the solution, exact solution requires C1 and C2 to be calculated. So what are the boundary conditions? So we need two boundary conditions. At x is equal to 0. Where is our fin? Let me show that fin. It's a constant cross-sectional area fin. At x is equal to 0 and at x is equal to L. At x is equal to 0.
So CP.
Yes. Here I'm saying this temperature is equal to some base temperature, fixed base temperature, to which fin is attached. T is equal to T, B. Okay. So, in other words, theta at B is equal to C1 e to the power 0. Okay. So, theta at B is TB minus T infinity, because theta we have defined as T minus T infinity. But now T is TB at the base. This is first boundary condition. Second boundary condition, what about at the tip at x is equal to L?
Have conduction.
Yes, one of the boundary condition which you are saying here, you will have conduction which is equal to convection. So one of the boundary condition is this one, minus k partial t by partial x at x is equal to L is equal to h into t at x is equal to L minus t. One of the boundary condition which we can use is this one. One of the boundary. But there are other boundary conditions possible. Okay, if this fin length, that is the length of the fin. If this fin length is very long, there is a fin attached to this wall. If this fin length is so long that here temperature at the tip is equal to ambient temperature. So this is one possibility. Second possibility, I'm saying that T at x is equal to L is T infinity for a very long fin. What is meant by very long fin, we'll see. There is a condition which ML product should be greater than something 2.65, then we can consider it a very long fin. Means T, yeah, 2.65, there is written somewhere. Okay. So then this is the second possibility. That is easier to solve than this one. Okay. Any other possibility? Third possibility could be that here is you have TB and here you have some fixed temperature. You want to maintain, or it is maintained by something. If you have fixed temperature, not T infinity, different than T infinity, but some fixed temperature. Third possibility, that T at x is equal to L at the tip is equal to some fixed temperature T. T at x is equal to L is equal to some fixed temperature. Okay. Fourth possibility. Fourth possibility is if it is insulated, the tip is insulated. What this mean? Yeah, but how it will be? For example, this is a wall or a pipe. This is another wall. And this is the fin. Yeah, there is wall or pipes and such fins are attached. Okay, so here you have TB, here is that fin. So at the center, from here to here, how the temperature will be dropping? Temperature will be dropping within the fin, like this, symmetric. So at the center, this dt by dx is equal to 0. This is what condition? Insulated. Symmetry, but what is here in this case? Dt by dx is equal to, or k dt by dx is equal to 0. What is that condition? Insulated.
That's a point.
Yeah, at that point, at that tip. So this is one way where we can say the tip isn't, because normally you never insulate the tip. Normally, we never insulate the tip. But if you have a wall here, if you have a second wall here, same wall here, like in this fin, have you seen the fins inside a refrigerator or a radiator? Those fins are attached to one pipe. The same fin is attached to the next pipe. It's one single with holes in it. So at the center of that fin, between these two walls, we can say dt by dx is equal to 0.
Not insulated.
Not insulated, but because of this, we can consider it as insulated. So that's why this fin equation can be solved for one particular boundary condition at x is equal to 0, but 4 different possible boundary conditions at the tip. So for each case, you will have a different equation. If you solve it like this, using first type of boundary condition at the tip, then you solve it again for the second type of boundary condition at the tip, third and fourth. You can have 4 different solutions for the same equation. And for constant cross-section area. Everything we are doing so far is for constant cross-sectional area. Fin, right? Second boundary condition may have these 4 different possibilities. We are considering convection. This one we are not considering, convection and radiation, both. Okay, otherwise you can answer.
The first boundary condition, always it will be the same, right?
The first part here?
Yeah.
Yes. That fin is attached to a base at one fixed temperature TB.
Yeah.
Okay, but at the tip you can have different. So first, if you say negligible heat loss from the fin tip means this one, insulated. Okay, so now you have to solve that equation using that boundary condition at the tip. First boundary condition is TB, and after doing this, finding C1, C2, putting it in the general solution, you will get such answer. And this whole derivation is here. For first case, for this one, if you say the tip is insulated, okay, this is the complete derivation step by step is here. This is the equation which you derived. for temperature distribution, and that is heat transfer. Then the second one, if you say no, it is not insulated, it is convection. Then the second one. This is very long. It ends up here. This is only by having C1 and C2 and putting it in the general solution and then simplifying it. Okay, which we can't do in the class. We do not have enough time. Okay.
We will not do the exam.
Of course.
We will only pass you.
Otherwise,
So we will come with vacation and go yeah.
it's there. It's simple mathematics. It's nothing which I have to explain you, because you know the mathematics. You have already done. So this is the equation you will derive. I have given you the derivation. So I've shared with you. If you are interested, you can go through the derivation. So then you get this equation for one particular condition when the tip is insulated. So what is this equation? It gives, what is time? Time is already over. Temperature at any x. This is the temperature distribution along the length of the fin. With the help of that equation, we can find temperature at any x when T infinity is given, TB is given, base temperature, and all others, M, L, whatever. And here there are hyperbolic functions involved. Okay. So we'll start.